All right. Good morning, everyone. 8:30. I anticipated this. This is actually one of my lowest attended class. It's doubly bad because it was Halloween yesterday. It's a Friday. It's kind of snowing out. So kudos to you all for being here. You hardy physiology students. Thank you. Okay, so I am recording this lecture. We will have some top hat questions at the end today, so you will get some points, I promise. So it is worth your while to come today. Thank you very much. All right. So let's get started. Today is all about kidney, right? Renal physiology. What we're going to do is we're just going to start off easy. Like I said, there'll be some top hat questions at the end, and I'll give you some brain teasers. So it'll be somewhat of a active learning exercise. I'll let you all talk about some of the things, the questions that I'm going to be posing. So let's talk about the kidney. First of all, how many of you know what the kidney actually does? Let's just start off really basic. You know where the kidneys are, right? Hold on just a second. The kidneys are actually towards the dorsal part of your body, towards your back, right? You have two bean-shaped kidneys, two of them, and you can kind of, if you actually feel back there, that's where your kidneys are. So if you have some kind of kidney infection or kidney stones, you'll probably feel it in your back. So you raised your hand first. What do the kidneys do?
Filters the blood.
That's right. All right? The main function of the kidneys is to filter blood, but it's all about the reason why it filters blood is it's actually regulating your blood ion concentration and water. Okay? So ion-water balance is a big part of what the kidney does. Ion and water balance. So what we're going to be learning about is, and again, I want you to reach back. We're going to be talking a lot about diffusion and osmosis again. I mean, with the kidney, this is actually key. That's why we started the semester off talking about diffusion and osmosis. Okay? All right. The other thing that I wanted to just mention is think about what your kidneys do as well. Some days you actually produce a very concentrated urine. Some days you actually produce very dilute urine, right? It depends on what your water concentration is in your body. If you just drank like 2 gallons of water, of course you're going to actually produce a very dilute water concentration to get rid of a lot of water in your body. But if you are severely dehydrated, your body has the capability of concentrating urine to help conserve water, okay? All right, so that's where we're going. We're going to learn how the kidney does this. We're going to actually dive right into what is a nephron, which is the single unit of filtration in the kidney, the nephron. All right, so here's an interesting term as well, retroperitoneal organ. So what does that mean? The kidneys are actually a retroperitoneal organ. So looking at the anatomy, your body, again, this is a cross section. If you took some kind of blade and just like cut through your torso, have you ever seen that Body Works exhibit that they had at some of the science museums? Yeah, so this is what we're talking about. You can actually see that your body has a peritoneal cavity, a coelomic cavity, all right? We actually have a peritoneum. You can actually see the membrane extends. This is the parietal peritoneum. Let's see here. Here's the parietal peritoneum here. And then the membrane, the peritoneal membrane that's closest to the organs is called the visceral peritoneum, okay? And you can see it actually surrounds some of your intestines, and it is basically facing the inside of your peritoneal cavity. Now your liver, your intestines, your liver and other organs are actually inside that peritoneal cavity, but you can see the kidneys are actually outside of that peritoneal cavity. And that's why it's called retroperitoneal. It's outside the peritoneal cavity. Again, towards your dorsal side, back. So, good term to know, retroperitoneal. All right, so let's take a look at the anatomy of the kidney. It is a crescent or bean-shaped organ, and there's two layers that I really want you to take notice of. I'm going to blow this up a little bit. Okay, you can actually see, and it's appropriate that it's Halloween, right? Because the medulla area looks like an upside-down candy corn, right? Everybody knows what those candy corns look like. They're these pyramids here. If you actually did a cross-section of the kidney, you would very easily identify the renal medulla, okay? So right here, looks like an upside down candy corn. All right, but the outer portion of the kidney is called the renal cortex, So these are two really important layers to be aware of, okay? Your glomerulus, we're gonna be talking about that filtration unit of the nephron, is actually located in the cortex region. And if you look at the osmolarity of the cortex region, it's very close to what your plasma is. It's about 300 to 320 milliosmoles, so very close to plasma concentration. But the renal medulla, these are where the loops of Henle are, of the juxtaglomerular nephron. We're going to be talking about that in just a minute. And the upper part of the medulla, again, is about 300 to 400 milliosmoles. But once you get down into the inner medullary region, which is right here close to the renal papilla, it can be as high as 1,200 milliosmoles. Very concentrated, lot of solute in that renal papilla. This actually helps you concentrate urine, that concentration gradient within that renal medulla area. And we'll learn more about that later on. So the kidney lectures are going to take about 5 different lectures, and we'll end up not next week, but the Monday of the week after, and then we'll start respiratory. All right, so like I said, we have plenty of time to go through some of the details of the renal medulla and the nephron. All right, so I'm going to blow this up one more time. Please know the difference between the renal cortex and the renal medulla area. Okay, so that the tip of the candy corn, like I just talked about, is also called the renal papilla. And your primary urine is actually modified in the nephron, in the tubes. As the fluid actually flows through the nephron, it's modified. But then that urine is delivered into this cavity right here. The first part of the cavity is actually called the minor calyx. So that's that little area right here, right next to the renal papilla. And then the urine flows into the major calyx. Okay, so that's this larger cavity right here. So again, urine is delivered across the renal papilla into the minor calyx. Calyces is the plural. Minor calyx first, and then into the major calyx. And then this V-shaped structure right here is called the renal pelvis. It's like the funnel portion. And then the urine is delivered into the ureter. So there's 2 ureters coming from each kidney. Let's go to this one right here. The urine is then delivered into the urinary bladder. And the bladder actually has a lot of smooth muscle associated with it. So during urination, fancy name for urination is micturition. During urination, the smooth muscle that surrounds the bladder is what am I trying to say? Contracts. Wow. It's one of those mornings. It contracts and then eliminates the urine through the urethra and out of the body. Through the urethra and then out of the body. All right, so I always try to give you what are the most common mistakes that students make. They do tend to, a lot of mistakes on exam 3 are mixing up the ureters and urethra. So they look very similar, but they are very different structures. Ureters and urethra. Ureters are transporting the urine from the kidney into the bladder. The urethra is the tube that transports urine from the bladder out of your body. All right, so moving on, let's go to this next one here. All right, again, taking a look at the anatomy of the kidney. You can actually see again the cortex region is the outer region. You can see this little bracket right here is pointing to the renal cortex. That upside down candy corn is the renal medulla, that pyramid. Most textbooks describe it as a pyramid. The renal papilla, minor calyx, major calyx, the renal pelvis, the funnel, and the ureter. Now, let's concentrate now on the nephron. This is way too big. It says enlarged. So your nephron are not this large, but the structure, this is a good way to look at the structure. You can see the glomerulus or the bulb is in the cortex region. And as I mentioned before, that loop of Henle dips way down into the inner medullary region and then back up. Okay, then they all have a common collecting duct, which then delivers the urine into the minor calyx. All right, imagine this, right? This, like I said, this is way too large. There's about 1 million nephron in each kidney, 1 million. Okay, so again, this is not representative of the size of the nephron within the kidney. All right, so a couple of new terms too. Again, this is an intro. You can always go back and listen to the video, but it's always good to kind of write down that terminology too. I'll try to put together a terminology sheet like I did for exam 2 as well. But there are 2 types of nephron that I want you to be aware of. 2 types. Let's start off with this one right here. You can see this nephron, again, has a common collecting duct. But the loop of Henle really doesn't enter into the medullary region. It's really confined in the cortex alone. This is called cortical nephron. Cortical. C-O-R-T-I-C-A-L. Cortical. And cortical is referring to the cortex region. So it's pretty much confined in that cortex. All right. The other type of nephron, and it is written right here, is called juxtamedullary nephron. Juxtamedullary nephron. Juxta means next to. Medullary is referring to the medulla. So in this case, you can see the glomerulus is still in, that bulb is still in the cortex region, but the loop of Henle dives deep into the inner medullary region and back up. And that's really important because it's these types of nephron, these juxtamedullary nephron, that are responsible for establishing that profound gradient within the medullary region. It's this loop of Henle of the juxtamedullary nephron that are responsible for establishing this very profound osmotic gradient within the inner medullary region. And that allows you to concentrate urine. That gradient. Yes, question.
Can I just have a bit more clarification on the loop of nephron and the difference between just the nephron?
Yep.
Are they the same thing, whereas the loop of nephron
Yep.
is an off branch of the nephron?
Yeah, so let me clarify that now. This is a really good question. We're going to dive into the anatomy of the nephron in just a second. But so the nephron in itself is the single unit of filtration, okay? So this nephron right here, the cortical nephron, starts here in the glomerulus. You can see the blood supply that actually enters into the glomerulus. This is where blood is being filtered. Yeah, this is a very good question. Okay, and then the entire nephron winds around. The loop of Henle is very short right here. It really doesn't go in the medullary region. And then it's delivered into the common collecting duct. You can see lots of nephron actually dump their urine into this collecting duct. And then it's delivered into the renal pelvis, right? The minor calyx, the major calyx, and then the renal pelvis. So this is one nephron right here. And then this nephron is a different type of nephron. Again, it's still the single unit of filtration. Glomerulus is here in the cortex, but the loop of Henle is very long, goes way down into the inner medullary region, back up to the cortex, and then basically delivers its urine into the collecting duct. Yeah?
So each collecting duct has like hundreds of...
Yeah, exactly. Each collecting duct has hundreds of nephron that dump their urine into that common duct. Now, we are going to be talking about the different blood supply that surrounds each of these nephron too. This one in particular is called the vasa recta because it has some special properties. Okay, the vasa recta surrounds the nephron, the loop of Henle, of the juxtamedullary nephron. Okay, so we'll talk more about that and its transport properties later. Okay, but the key idea here is that you have two types of nephron. These are the single unit of of filtration. Got to get out of the muscle unit here. All right, you can also see that you have arteries and veins, right? The arteries branch into arterioles. Arterioles actually are what enter into the glomerulus. You have afferent and efferent arterioles. And this is where the blood is filtered. We're going to get to that in just a second, too. All right, so again, I always tell you these are some of the slides that I want you to star. This is a very important slide. You'll see it over and over again, but this gives you very good information breaking down the anatomy of the nephron. All right? I'm going to call this the tubular tour. We're going to go through the tubular tour. All right. So what we have here is, first we're going to start off with the glomerulus. Again, this is the nephron, the single unit of filtration. All right? The blood that flows into the glomerulus, this is coming through a tube called the afferent arterioles. Afferent, remember we use that term with neurons. Afferent is bringing a signal, or in this case, blood, to the glomerulus. Efferent arterioles are bringing blood away from the glomerulus. So the efferent arterioles are transporting blood away from the glomerulus. Now, this is kind of a this is not correct. All right, so take a look at this. This shouldn't be blue. All right, this is not deoxygenated blood. This is still an arterial. All right, so I would put a little arrow and say this should be red. Yeah.
So are there separate capillaries that'll deliver blood to the kidney?
Yeah.
For oxygenation purposes?
Yeah.
Transporting oxygen?
Right. That's a really good question. So are you asking, is there just one arterial per glomerulus?
I guess.
Yeah.
Also, if there's just like a separate system that delivers blood to just give oxygen and nutrients to the cells.
Yes, and that's the vasa recta. Very good question. So going back, let's put everything together here. The question was, what is actually bringing oxygen and nutrients to the epithelial cells of the nephron? And it is this paracapillary, these paracapillary vessels, and it's the vasa recta. Okay, so it's not part of the arterioles that are going into the glomerulus. So it's important to note that you do need blood to actually perfuse the epithelial cells of the nephron. These epithelial cells have high active transport properties, and you need to have oxygen and nutrients just like any other cell type. And it's the vasa recta that are actually supplying the oxygen and nutrients to that portion. All right, but the glomerulus, those afferent and efferent arterioles right here, this is just about filtering blood. All right? So blood is forced out. We're going to talk about Starling forces again. That's what we ended with the cardiovascular section. So the pressure has to be, the hydrostatic pressure has to be very high in these capillaries. Forces fluid out of the capillaries into the proximal tubule. So we'll talk about the anatomy of, we'll get to the details of the glomerulus in just a second, but this space right here is called Bowman's space. The fluid that's forced out of the capillaries into Bowman's space is actually very isosmotic, meaning it's very plasma-like. About 300 milliosmoles, like I said before. Now, you're forcing a lot of really important things into Bowman's space. You're forcing nutrients like glucose and amino acids. All of your electrolytes from your blood is being forced into this Bowman space. So it makes sense that the next tube that's really important is called the proximal tubule. Proximal meaning next to. It's very near the glomerulus. All right, so if you only think about one word with the proximal tubule, think about reabsorption. Reabsorption. So reabsorption means that you're pulling out very essential molecules. You want to recover them and bring them back into your blood. You don't want to lose them to your environment, in your urine. So reabsorption means that you're pulling molecules out of this tube. It's being transported across the epithelial cells back into the blood, being recovered. You don't want to lose that stuff. So 100% of your nutrients include glucose and amino acids, are being saved. They're being pulled out of the nephron and brought back into your circulatory system, back into your blood. 85% of bicarbonate, which is your main buffer in your blood, is being recovered or reabsorbed. Bicarbonate is being pulled out of the nephron and brought back into your blood. 70% of sodium and potassium are also being recovered, and 70% of water. So all of these things are being recovered. They're being pulled out of the nephron, almost being saved, being pulled out of the nephron and delivered back into your blood. So proximal tubule is all about reabsorption. Then I'm going to call this the primary urine because it's not really urine yet. It's going to be modified throughout the nephron. The primary urine, or what's also known as ultrafiltrate, not called urine yet. That fluid is being modified as it goes down deep into the inner medullary region. Imagine it flowing down through the tube. and it is encountering an environment that is more and more hyperosmotic, more and more solute in the environment. So what that tends to do is it tends to pull water out of the nephron. This is just by simple osmosis. As the fluid encounters a more hyperosmotic, it's going to flow out of the nephron. And solutes are going to flow into the nephron, right? This is very highly permeable to both water and solutes. Water's going to flow out and solutes are going to equilibrate. They're going to move in and out until it's about the same inside and outside. So here in the nephron, it's about 1,200 milliosmoles, very concentrated. That very concentrated fluid moves up the loop of Henle into what's known as the thick ascending limb, TAL, thick ascending limb. This is actually a really important part of the nephron. It has very special properties. That's why it's in blue right here. It's called the diluting segment. Why? Because it has my favorite co-transporter. I don't know if you remember way back, it has that co-transporter, the sodium-potassium 2-chloride co-transporter. It's moving a ton of solute out. Remember, this is pretty concentrated fluid. It's just moving solute out, more so in the beginning than up here at the top of the thick ascending limb. So it's moving solute out, but water is not allowed to follow because there's no pathway. It's very low water permeability. So water stays inside this tube, which is why it's called the diluting segment. It is actively pulling molecules out, solute out, and it doesn't allow the water to follow. Okay, so it's very dilute, only 150 milliosmoles at the top of the thick ascending limb. Okay, now we'll talk about there's some really dynamic regulation between the glomerulus and the distal tubule here. That's right after you get out of the thick ascending limb, you enter into this area called the distal tubule. And there's some regulation, crosstalk, right? There's some signaling that goes on that really has some effect on flow in the glomerulus. Glomerular filtration rate. All right, but we'll talk about that later. The fluid then continues on through the distal tubule. This is where a lot of sodium and chloride are still being reabsorbed. But in this case here, a lot of potassium and acid are being secreted. That means they're being delivered into the nephron to be eliminated, to be forced out of your body when you urinate. So you produce a ton of acid on a daily basis, a lot of acid, especially think about when you exercise, you build up lactic acid, sulfuric acid by metabolism of different amino acids. You produce a ton of acid on a daily basis, so you have to get rid of that. This is where a lot of acid secretion occurs. And then we'll also talk about vasopressin, arginine vasopressin, and urea. Vasopressin is a really important hormone that allows you to concentrate urine, and we'll talk about that regulation. But again, in the collecting duct, remember this is a common collecting duct. Lots of nephron, they deliver their urine into a common collecting duct. Again, a lot of sodium chloride absorption, reabsorption happens here. Potassium, proton, acid secretion happens here, just like in the distal tubule. You get complete bicarbonate reabsorption, normally. And then regulation by vasopressin. Then the urine, now that it's been modified and delivered into the renal pelvis, then we can call it urine. So again, these are tubes. The nephron are tubes that are lined with epithelial cells. That's why we went through epithelial cells that have these active transport mechanisms that are modifying the fluid within each nephron. Okay? So again, a very important slide. If you need some text associated with what I just talked about, this is a really nice summary of the division of labor in the renal tubules. So let's talk a little bit about comparative physiology. When we're talking about different species of animals, you'll notice that there is a major innovation within the kidney, and that is the loop of Henle. Right? As animals evolved, the loop of Henle has evolved to help animals concentrate urine. Okay, so the loop of Henle is what allows for animals to produce a very concentrated urine. So aquatic animals like frogs, beavers that are around water all the time, there's no need for them to concentrate urine, right? They have a rich supply of water and they never have to concentrate urine, never dehydrated. So you can see here, most of these animals have a very short loop of Henle. In fact, frogs don't even have loops of Henle. But let's go to the other extreme. Let's just go to C here. The kangaroo rat that actually lives in a desert environment has one of the longest loops of Henle. They hardly ever urinate because they have to conserve water all the time. They also have a very pronounced medullary region and a pronounced renal pelvis. All right, so let's actually talk about the 4 different processes of the kidney. This is something we'll be concentrating on in the next couple of days. The 4 processes of urine production are, number 1, filtration. Filtration happens in the glomerulus, and now we'll go into detail about the glomerulus, the anatomy, and what it does. We also already just mentioned reabsorption and secretion. Reabsorption is when it is a process of pulling water and solutes out of the nephron and recovering it, delivering it back into the blood supply. Secretion is the opposite. Secretion is actually taking molecules and fluid from the blood and delivering it into the nephron to be eliminated when you urinate. That's secretion. Excretion is the process of urination. Micturition, excretion. All right, so first let's focus on filtration. All right, so this is a really good, we've zoomed in on the glomerulus. This is a good diagram that kind of sums up the structure. Okay, so here the afferent arteriole is on the right-hand side. All right, so the afferent arteriole is bringing blood into the glomerulus. These are known as the glomerular capillaries. And these are under really high pressure. These podocytes mean like foot processes. These are specialized structures that form these filtration slits, and they can be modified. The slits can close or they can open to allow for less flow or more flow. Okay, so it's kind of regulating the flow. Filtration occurs, right? Fluid is forced from the capillaries into this space here called Bowman's space, and then forced into the proximal tubule. The remaining blood in the capillaries flows out of the efferent arterioles into the renal vein. has to go through the vasa recta, right? That perfuses the nephron, and then the renal vein, right? We'll talk more about these cells, juxtaglomerular cells and mesangial cells. They have regulation, and here's the distal tubule. Remember, there is some signaling that's happening here, intrinsic mechanisms that are regulating the flow into the Bowman space, but we'll talk more about that later. All right, so again, some terms, right? Here are some texts to help you with summarizing what I just talked about. Liquid components of the blood, plasma, escape into Bowman's capsule, but the bigger blood cells and larger macromolecules like albumin are not filtered. They actually stay in the capillary. So this only occurs in the glomerulus because these glomerular capillaries are very leaky. Now, I'm going to bring you back to the cardiovascular section. Remember, these are fenestrated capillaries. Fenestrated. And that's why they're leaky. Those podocytes, foot processes, form the filtration slits. And when we get to intrinsic mechanisms, we'll talk more about the mesangial cells that actually control the filtration, those filtration slits, and the flow within the glomerulus. All right, so now let's revisit net filtration pressure, right? This is what we talked about at the end of the cardiovascular section. I'm going to skip to this one here because it gives you some numbers, all right? So here's the glomerulus again. We have the glomerular capillaries, and here's the glomerulus itself and Bowman's space, okay? So here's a little box right here. This is what we're zooming in on. And you can see this is the box right here. We're zooming in. This reddish portion is what's happening inside the capillaries. And then this yellow portion is Bowman's capsule, Bowman's space. And there's actually some interstitial fluid in between. Now, remember we talked about oncotic pressure when we were talking about the cardiovascular section and net filtration pressure. Oncotic pressure is the osmotic pressure due to the protein concentration within the blood, those larger blood proteins. So, the flow, the pressure that net filtration pressure is determined by three main forces. The glomerular capillary hydrostatic pressure, Bowman's capsule hydrostatic pressure. Remember, those were P. In this case, we're going to use PGC, glomerular capillaries, and the hydrostatic pressure of Bowman's capsule, or BC. And then the oncotic pressure of the proteins within the glomerular capillaries. So here is our equation again. Net filtration pressure is equal to the glomerular capillary pressure minus the hydrostatic pressure in Bowman's space minus the oncotic pressure in the glomerular capillaries. But what happened to the oncotic pressure in Bowman's space? What happened? What do you think? Why could we take this out of the equation? Oncotic pressure in Bowman's space. Yeah, you can guess.
Probably because water isn't able to go slow from
You're close. You're close. It's not water, but you are filtering plasma. But you shouldn't be filtering any larger blood proteins, right? You shouldn't be filtering any larger blood proteins. So the oncotic pressure in Bowman's space is 0. You can take that right out, unless there's a pathophysiological state. If you have some kind of kidney infection and bacterial infection that has disrupted the integrity of the filtration unit, and you're losing blood, you should never have blood in your urine, right? You losing blood into Bowman's space, then that's going to disrupt this net filtration pressure equation, right? Then you have to actually add that oncotic pressure in Bowman's space. All right, but under normal situations, under normal circumstances, usually the oncotic pressure in Bowman's space is 0. All right, so then we can actually, run the equation, right? The hydrostatic pressure in the glomerular capillaries is 60. Now think about that. The hydrostatic pressure in the vasculature in the capillaries is usually only 30 to 33. This is twice the hydrostatic pressure in the glomerular capillaries. So again, it is under high pressure. Subtract that from the hydrostatic pressure in Bowman's space. That would be 60 minus 15, that's 45. And then subtract the oncotic pressure due to the larger blood proteins in the glomerular capillaries. That's oncotic pressure. So 45 minus 29 is 16. Remember, if this is a positive number, then filtration will occur. So again, that's going to force fluid out of the capillaries into Bowman's space. Now it's still pretty much under high pressure. This is the pressure that is driving the fluid through the entire nephron. You have to move that fluid through the entire nephron into the renal pelvis. So that's why this starts out at such high pressure. We'll talk about these 3 intrinsic pathways and extrinsic pathways next Friday. By the way, don't clap, you'll hurt my feelings, but I am going to be out of town next Friday, so the lecture is actually going to be recorded. There will be a quiz afterwards. So no class, you won't be physically here next Friday, but just so you know, you'll still have a lecture, okay? All right, let's get to this fun part. We still have a few minutes here. So again, almost like cardiovascular, the renal system is about plumbing issues, Okay, so think about our garden hose physiology, going back to Ohm's law. Driving force is equal to flow times resistance, right? So I'm going to give you some physical intuition here. This is, like I said, just plumbing, all right? Glomerular filtration rate, which we're going to go into a lot more detail next week, is flow. This is a flow. All right, so this is actually what flow is across the glomerulus. P is the hydrostatic pressure in the glomerular capillaries. This is pressure. All right, so let's blow this up. I'm going to start here at the top left-hand corner. I'm going to blow that up a little bit. If you constrict the afferent arteriole, what that does is it lowers the pressure in the glomerular capillary. It lowers the hydrostatic pressure in the glomerular capillary. That actually decreases the flow. Okay, makes sense? This is intuitive to some people, but I need to walk through because there's one of them that when I was a student, I really had a hard time with. But this is going to decrease glomerular filtration rate or flow. Now, the opposite is true if you constrict the efferent arteriole on the back end. If you constrict the efferent arteriole, upstream the pressure is going to rise. You're going to increase hydrostatic pressure in the glomerular capillary. That is going to increase flow or glomerular filtration rate. Now, this is where it gets less intuitive. The opposite is going to be true if you dilate the efferent arteriole, right? If you dilate the efferent arteriole upstream, the hydrostatic pressure in the glomerular capillaries is going to fall and flow is going to decrease. The opposite is true with dilation of the afferent arteriole. If you dilate the afferent arteriole, you get more blood to flow into the glomerular capillaries, increasing the hydrostatic pressure and increasing the flow into Bowman's space. Okay, so this is something that you have to kind of mull around. Remember that there are intrinsic properties, regulation, that are going to dilate or constrict the afferent or efferent arterioles, which are going to control glomerular filtration rate. All right, reabsorption. That was filtration. Reabsorption is, again, depicted as number 3. We're going to start with number 3. Whenever you pull solutes and water out of the nephron and deliver it back into the blood, that's called reabsorption. Remember, there's a lot of different membranes that this occurs, right? If you actually pull solute out of the nephron, it goes across the basement membrane, interstitial fluid, endothelial cells, and then back into the blood. So we're missing a lot of steps here, but you can see that a little bit better here. Solutes and water are transported across the epithelial cells into the interstitial fluid, across those endothelial cells back into the blood. So I want to make sure everyone realizes that as well. Most of the reabsorption happens in the proximal tubule. Don't forget about that. And most water and salts are reabsorbed using transport proteins and energy. Secretion is the opposite. Okay, secretion is when you deliver drugs, vitamins, potassium, ammonium ions, and acid from the blood, and you deliver it into the nephron to be eliminated when you urinate. So that's secretion. It's similar to reabsorption, but in reverse. And it also requires transport proteins and energy, like secondary active transporters. All right, so let's have a little game here, right? Let's take a look at, if I say to you, which substance is filtered at the glomerulus and strongly secreted. Which one do you think it is? Let's do a top hat question here. Really quick. You guys get some points today. All right. Oh, by the way, here's some statistics. I almost forgot. This is from the Proctorio group. The average was high, 82, which is great. Sorry, I didn't show you this earlier. Here's the distribution. I should have all of the paper copies graded today so you can take a look at it. I'm going to open it up so you can see your scores today, later today. Okay, so top hat, let's get this in today. All right. Taking its sweet time. There we go. We got one more minute. Let's get this in here. All right. Steeping tea, steeping tea. That's what it says. Steeping some tea. All right, so sorry. Let's get to this question here. There we go. So the question again is, looking at that figure, Which of these substances is filtered at the glomerulus and strongly secreted? Is it the first one on the left, substance X? The middle one? Yeah.
It's not showing up.
Oh, the picture?
No, the question is not showing.
Oh, darn it. Okay, I still want to give you all points for today. So what I'm going to have you do is if you just write it down on a piece of paper and turn it in, I will give you points today. So it's not working, huh? Top Hat is just dead. All right, wow. Oh, it's okay. All right, just took a while. Woohoo! All right. Okay, so we only have like 3 or 4 people. You know, we're already out of time, so if you've answered and you feel confident that it's actually registered, have a good weekend. Yes. Have a wonderful weekend. We'll pick this up on Monday. But you might want to hear the answer. Yeah. You might want to hear the answer. Anybody still having trouble with their Top Hat? No? All right. All right, so the answer, how many need a little more time in this room? Pretty good? All right, then the correct answer is X. It's A is the right answer. Substance X. All right, so remember, secretion is pulling molecules from the blood into the nephron to be eliminated with the urine secretion. Hi. All right, have a wonderful weekend. Cynthia.
I don't see her. So, let me just.
It's all good. My office hours are extended either way.
And
so
where are you?
Right across the hall.
Okay, you're in the.
15, yeah.
Yeah.
In the lounge.
Okay, sure.
There.
You'll have to come with me to get a copy of the exam.
Oh, right. I have a class now, but I could stop by after.
Yeah, that sounds
Because
great.
I get done at 10:25, so I
Okay.
can come straight to your office.
That sounds great.
Did you have any, like, I suppose I could check when I come to your office, the tired swimmer problems that
Yeah,
a
let me.
couple people were missing
I know.
those.
Courtney.
Yeah.
Yeah. Okay. So I will track those down.
All right,
Okay.
sounds
Yes.
good.
Thank you. Yes. Yeah. Whatever one you want. Yeah. You're welcome.
Hey, sorry.
Oh, no worries.
I was wondering if you ever got the exam corrected or.
Yours?
Yeah.
Not yet.
Okay.
I know. I'm so sorry.
It's okay.
I have about 32, and I have those at the. I will get those done
Okay.
today, though.
All right, okay, thank you.
Yeah, you're welcome. Oh yes. Okay, hold on just a second.
Yeah.
So I know, and that is totally